All right, welcome everybody to week 2, day 2 for IS50B. I just went over with the IS50A people this new site that I found, and it's not a new site, it's just new for me. Internet's a big place, right? So I found this place called Polyhaven, which has free stuff you can use for your games. It's got some really nice, really high resolution stuff, HDRIs, high definition, rendering things you use for skyboxes and things like that. And it'll look really nice. Textures though, in IS50A, when you took it, I think we made a material together, but this actually gives you some nice stuff to make materials out of. So you can come in here and go leather red, and if you look at the thing here, you can see it's got a roughness map, a normal map, color, different colors, same color. Why is there two different colors? Oh, there we go. And ambient occlusion. Ambient occlusion is self-shading, right? A normal map is what direction the individual fibers are facing, really. And the roughness map is which areas are rougher and which ones are smoother. And so it's got a nice 3D preview. You can zoom in on it and see that it's got like some pixels are shiny, some pixels are not. It's got a nice little textured surface. And you can just download all of them. You don't even have to log in at all. Download them, and then you'd feed, here, I'll just go through it again, because I don't know if you guys saw it or not. So let's do this leather thing here. I'm going to save the zip file there. And I just quit out, didn't I? Why do I have two summer 2020s? I need summer 2021. There we are. Okay. Yeah, so you just download those things, and they're just going to be different images. It's going to come in a zip file, so you just unzip it. Come over here, and that. No. Okay, so that's the snow one. Do that. So we got the leather thing here. We're just going to unzip it. Refresh. There we go. And then we will just drag these into our content browser. Minimize, Unreal Engine, here we go. Okay, so we're going to build, make a new folder called leather mat. And I'll just drag all this stuff into here. It's going to go through the import process. Pulls the 3 textures in. And then we can right click, make a material. This is all stuff I know you guys know already, but like I said, it's a cool site that I found. I'll call this red leather map. Reed leather? Red leather. Okay, there we go. Open it up. Snap it over to the right. You're going to import these 3 texture samples into it by selecting them, dragging them in. Come over here. And we've got the 3 texture samples in here. This is the color. Sometimes people call it diffuse. Sometimes people call it albedo. In Unreal Engine, it's just called base color. So the name of the file is leather red coal 1, so I assume that means color, so look that up there. This one here is leather red roughness, so we're going to feed that into the roughness pin there, and then this one's obviously going to be the normal map because it's a weird holographic color, so we're going to feed that into normal there. And this is importing an already created texture, yeah. So basically, the hard thing for me is that, like, I'm not an artist, and so I don't have the ability to make, these noise patterns and things like that. I need to find somebody that's done it. If I have a noise pattern of like cracks and crevices, I could probably use a lerp and a blend or something like that, or a multiply to start putting together, something that'll work for like a couch or something like that. But that website, it's got the maps done for you. So it's already got a normal map, it's already got a roughness map, it's already got a color map, and you just plug them in, boop, 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 like that, hit save. And then, is the landscape still screwed up? Yeah, my daughter moved the landscape, so let's move it out of the way. There. Almost right. Needs to go here, maybe. That's too far. Too far that way. My daughter moved the entire landscape and didn't realize it and saved it, and so I'm trying to find the place where it's supposed to be. That looks like about right to me. Okay. Oof. That's about right, I guess. Everything's screwed up, huh? I don't know how that happened. Yeah. I think she like started adjusting it after she moved the landscape. So no matter where I put it, it's going to be off in some direction or the other. Okay, anyhow, so we just made the thing. So let's, this is like everything's off. Man, that is rough. Everything's off. Maybe I have to move it this way. It's a little better. Maybe we should move it in 2 axes. I can probably use the Stonehenge to figure out where it's supposed to be. So Stonehenge is supposed to be right on the top of that hill there. Like that. Yeah. Alright. Cool. That looks good. Hey, look at that. The waterfalls are back. That one's gone, but fix it probably. And let's see if this one over here is right. Oh, that waterfall's back. That's good. And the land is not inside of the hotel anymore. Cool. My daughter's going to be very happy to see this. So let's hit save. Because I think she moved some of those waterfalls trying to fix it. So I'll let her fix those back. And that looks pretty good. Yeah. So my daughter does Unreal Engine for fun. Like, she built this whole thing in about an hour with the temple and the waterfall and things like that. It looks pretty nice. Okay, so we just made a red leather surface. So let's just go ahead and apply it to the Stonehenge here and create a leather Stonehenge. It's very shiny, huh? Look at that. We need to probably do something about how shiny it is. Looks like it's made of marble, like a red marble color. So specular. Let's just turn the specular down to 2. And that roughness, man, that roughness is super. I don't know. Let's just try turning the spec down and see if that helps. It's still super shiny. I wonder if it's like inverted or something. Minus, subtract. Probably inverted another way. Maybe not. Okay. Roughness. So I'm going to actually reverse the roughness where this is white, I want it to be dark, and where it's dark, I want it to be white. Let's see if that fixes it. Yeah, it's looking a little better. The color's a little weird. At least it's not super shiny anymore. It looks like mahogany now. Not bad. So, it's because it's, I don't know what's going on. Okay. So, got back from the library. I believe we got some gaming laptops ready. Cool, cool, cool. Nice color representing blood. Yeah. So, yeah, basically that website seems to have a pretty good collection of texture samples, and that's again something that I can't make. I just need to find other people doing it. So that's a good resource for y'all. And then there is also interesting. Yeah, so you can try that. I don't know if that's the one that I was thinking of, though. Free assets. There's the free audio files that I think I've showed you guys before. Free sound files. Yeah. And so this one is a good site for getting free sound effects off things. I think you have to register to use it. Is this it? Yeah, this is it. You have to log in to access it. But they got tons of free sounds on it, so that's a good site for sounds. And then that Poly site there is good for. Let's rebuild the lighting while I'm talking. That Poly site's good for pictures and models apparently. So cool, tons of free stuff. What was the other one I was thinking of? Oh yeah, the Humble Bundle. Some of you that had me last semester saw that I purchased a Humble Bundle. No, it's not that. See Unreal Projects, which is a totally separate thing. Unreal Engine. This is the source code for the Unreal Engine. That's not it. Where did I put it? Unreal Engine projects. Take 3. Intro to Unreal Assets. Nope, not you. Game development. I don't know. I'll have to find it. I downloaded a ton of assets from where was it? You could probably look at my video from last semester because I found it then. I put them somewhere. They're somewhere. Splatter ink blot texture. Cultist 05. Yeah, that's the name of it. So let's just search for that somewhere. Control-Shift-F. No, really, it's not set to find. Search. I'll find it while this is running. Key shown folder from Google Downloads. I think it's been too long since I have Cultist 05. I'll just let that run. That is find file location. Aha, old desktop. Why the hell would I put it there? Okay. Character avatar icons. What the hell is it doing there? Okay. Okay. Oh. Just put into here, I guess. New folder. Art assets. I really need to just reorganize how all this stuff saves, so all my art assets can go into one place. And so you can download from Humble Bundle things like this that have tons and tons of art that you can use. And they usually go up pretty cheaply when they go on sale. If you buy these all legitimately, it's very, very expensive. But if you get the Humble Bundles, you get thousands and thousands of bits of artwork that you can use in your games for free. So that's another way you can get assets into your games. Like I said, I'm not an artist. I rely upon things like that. Okay, so it's still doing the lighting. So okay, let me talk about your next homework assignment. I want you to make a bot that runs around inside of the world. So we've been using the third-person template. You should be able to make a character. A character is anything that sort of autonomously moves around inside of the world. A character is something that has a movement node. So, dang it. Those people are probably below the world. No, they're over here. Good. Good. Everything's back where they should be. Excellent. So this here is a character. And if we edit the blueprint for it, you'll see that a character has a movement associated with it. So things that are going to move themselves around, not cheating like I do with the boxes. The boxes literally just change their position every frame and move towards the player, which is kind of lame and doesn't interact with the world correctly. If you want to do it properly, you create a character. Characters come with a character movement. Character movement over on the right-hand side here controls things like their speed and their gravity. You know, you can have it affected by gravity more or less. Default, it walks. In water, it default swims. And so, how fast does it run? How fast does it run when it's crouched? You know, all these kinds of things. Its step size, yeah, there it is. Its step size is in here. So how far can it step up? If it runs into a wall, can it step up on top of the wall? Well, it depends how tall the wall is. In this case, 45 centimeters is the maximum wall that it can just boop, go up to the top of. How steep a cliff face can it go up? 45 degrees. Okay. So any character you create will have all these things set, and you can obviously tweak them to your heart's content. Air control is how much you can move when you're in the air. That's pretty important in some video games, like in Mario Brothers, when you jump off a ledge, you can turn around and jump and move backwards. And that's air control. So yeah, this is what I kind of want you guys to do. Something like this. So I want you to make a character, put it into your world, and I can even just screenshot this for y'all, and have it run around. Okay. So let's put that out there. So what's going on? Every tick, this little bit here is checking to see if it's time to run again. So every tick, it checks to see if it's ready to think again. If it's not ready to think again, it doesn't do anything. If it's ready to think again, which is set by this variable here, AI update, not all update, AI update, once every 5 seconds it will think. And last moved holds the last time that we moved. And so every time we move, we set last move to the current time. We set it to the current time. And then every tick, we check to see if it has been more than 5 seconds since the last time we thought. Are you guys familiar with this code pattern? I'm sure you guys have seen this before, right? When I've done blueprints. Basically, every tick, you check to see if it's ready. Another way you could have done this is with a timer, which is probably the better way of doing it, but whatever. So every tick, it just checks to see if it's ready. If it's not, it doesn't do anything. It's not too expensive. As long as we don't have thousands of these things, it's fine. So if it's ready to think, then we will flip a coin. So random float in range is going to flip a coin. So it's going to pick a random number from 0 to 1. If the number is bigger than 5, then it will do this thing. If it is below 0.5, it will do this thing. And so both of them are move 2. So this is something that uses a nav mesh. Okay. So the first step that you're going to have to do in your third-person template is put a nav mesh over the world. How do you do that? Well, the lighting's still running here, so I don't know if this is going to work. But over here in the Place Actors tab, there is a nav mesh bounds volume here. You drag that out into the world, which I've already done. And I actually just expanded it to encompass the entire world. And you can use the scaling tool and just, I just have it encompass the whole world so that AI can navigate anywhere within it. Ooh, look at that. Let's increase the camera speed up a lot. Come down here. Look at that, the water is not good anymore. Ooh. It's going to invalidate the lighting, isn't it? Whatever, undo. So, if you want to see the nav mesh, you can hit P. The P character will show the nav mesh. That's how you know that it's worked. It's a bit flaky, honestly. I was teaching this class a year ago fall, and I was just showing students how you can change the options on a nav mesh and things like that, and it just turned off. Like I think it changed like the step height, which is like the maximum distance that an AI can go up when you're walking forwards. Because a step is not a ramp, right? It's a wall. So you're technically running into a wall every time you run into a step. And so there's a step height that says if you run into a wall, if it's within 45 centimeters, instead of stopping, move up onto it. And the nav mesh here, if you have it selected, has different properties. Yeah, the recast nav mesh, that one. So it's got all these different properties. Max slope 44 degrees you can walk up. Max step height 35 centimeters. So I think I probably changed that to like 45 just to make it match the character movement. And then you can see it recalculates the nav mesh after that. I changed it and it didn't work. And then I changed it back and it didn't work again. I was just like, what the hell just happened here? Like, it's the same. I hit undo twice and nope, it just stopped. It just literally turned itself off. So just be aware that, and this was a couple of versions of Unreal Engine ago, so it might have been fixed. I don't know. But just be aware that if you hit P, you should see green appear on all the areas that are navvable, which means areas that the AI can walk to. So the AI thinks it can walk over to this roof, actually, probably by, or I guess if you're on the roof, you can walk on it. But these areas here are too steep because it's greater than the max slope, so it will not walk onto this area here. But if you put the AI onto here, it would randomly walk around on the roof. I don't think it can connect to the rest of it. You need to use something called a nav mesh link to nav link proxy to teach it that it could jump from like the roof to the ground and things like that. So I'd like for you to all, step one, make a nav mesh bounds volume, have it encompass your entire world. Some people might say don't make it encompass the entire world, only make it encompass the area that you want the AI to be able to walk around on. But for me, it's like if I put an AI here, I want it to be able to walk around on the second floor of the hotel. So, whole thing seems fine. It recomputed that entire thing pretty quickly, right? So, doesn't seem too bad to me. You can hit P again, turn off the nav mesh, and Look at your lighting. You are terrible. Shadow and direct only, please. Okay. In the landscape, we'll get these weird lines on them until you redo the lighting. All right. Save. So step 1, put out the Nav Mesh and size it to fit your entire world. It's easier that way. There we go. Lighting's done. Hopefully I didn't just invalidate it again with that thing. Yeah, okay, that's fine. All right, cool. This looks a little, no, it still looks garbage. Probably need to redo the lighting again. Yeah, these trees have bad UV mapping on them, so you have to sort of play with the settings on them. But we got shadows again. Yay, we got shadows. Oh, these are floating, aren't they? We're gonna have to fix that. Oh, that's also off. Oof. Yeah, there's more fixes we need to do here. Oh. So, yep. And then for the next step, you're going to import a character of some sort, or you can make a character from scratch if you'd like. And I need to really turn down that camera speed. So the next step is to import a character. I imported one of the Unreal Engine's or Unreal Marketplace things. Let's see if we can find the thing here. So we go into the library. There are a bunch of Paragon assets. And the Paragon assets are pre-made characters that are gargantuan. They're like 5 gigs each, something like that. And there's a bunch of characters there. You just drag one in. I use Decker. You can use anyone you want. You just add it to the project. Come back after you've downloaded 5 gigs of data, and then you put it into your world. Then you wait another half hour for it to compile all the shaders for it. And at the end of the day, what you're going to do is for the character. Remember, characters are things that can move around. You're going to do this, and so every tick, it's going to see if it's ready to think again. If it is, it flips a coin, and I mean, you don't have to make it flip a coin. That's also not something you have to do. You can mix it up, and I encourage you to mix it up. But what I'm doing is I'm flipping a coin, and then this blueprint is running on the Decker AI character. And so what it's doing is that it's getting the controller. So a controller is the thing that moves a character. So for a player, it's like, you know, maybe actually a physical controller or something like that. But you can't actually move players the same way that you move normal objects. Like if you try setting their position and things like that, it doesn't work because the controller is moving it. So if you want to move an AI, you have to use commands like move to. And there's various options of move to. They use the Nav Mesh. And this is the full one here. So you plug in the controller on the controller slot, of course. Controller object reference not compatible with AI controller object reference. Probably have to cast it or something, doesn't matter. So you then give it a goal that is the location it wants to move to, or the actor you want it to move to, and the easier way of doing this is to use the simple ones, right? So plug in the controller, and the goal, which is the actor that it's going to move to, is the player character. So the Decker AI bot that I made, half the time she will run towards the player. And so she'll pathfind around obstacles and things like that. It looks really cool. And then the other half of the time, she's going to move to a random location near her. So she gets her location in the world. This is pretty cool. Get random reachable point and radius. So it uses the nav system, and it finds just a random point somewhere near you. If we were to put her on the roof of the water temple, she would find a random spot on the roof. It doesn't find a random place in the world. It just finds a spot she can walk to. And then it returns a random point that she's navvable to. And then we say, controller, move towards that point. And that's it. It handles the rest. Okay? So if we save... Did I save it? Let's close that out. Let's go ahead and put her on the. Let's click. There. I'm holding down Shift so the camera slides with her. It's easier this way. I'm just going to stick her on the roof over here. Like that. And hit end. Oop. Oh, she ended up way down there. Okay. Let's put her up a little bit higher. And then end to drop her down. The scale of this temple is really deceiving. It's really quite big. Okay, so she's on the roof now. And so if we were to come over in the world, and I need to add sprinting. Walking so slow. I really need to add sprint. No, I keep hitting Shift to run faster. Okay, so if we were... boxes are coming in at me. So if we were to look at her over here, you can see she tried navving towards me. Ah, box. Terminator boxes. So you can see some of the time she's navigating towards me. And then some of the time she's running around randomly, right? So right now she's running towards me. See that? She's trying to get as close as she can towards me. And then if she flips the coin and picks a random spot, she runs there, and then she'll start running towards me again. See? Then she picks a random spot. Picks a random spot. Kind of cool. So that's what you have to implement by Tuesday. Okay. those boxes are pretty intense. My daughter hates them, so I cut them down to just 10. After you kill 10 of them, it stops. But they come right through the walls. They do not use the nav system. They are hard coded to just move towards the player every frame, and so they bypass collisions. It's a little scary to deal with. So yeah, just make a bot, and if you want, you can make it so that when she hits you with a spear or something, you die, or I don't know. But a little water lilies down there. That's cool. Yeah, but that's your thing. Okay, so you're gonna add a Nav Mesh and have an AI kind of randomly move around on it, and that'll be due on Tuesday. Okay. Then that's not the end of class, even though it sounds like the end of class. There is some mathy stuff that I do want to talk about. All right, any questions about this? The blueprint that I use is on there. You're free to use it. I would recommend mixing it up a little bit. Like do something cool. Maybe maybe play an animation. That could be interesting. Where did her blueprint go? There we go. Blueprint. Maybe we can play like a different animation or something. Animation. Mesh. I don't know. Mesh has an animation blueprint. I don't know if that'll work actually. It's got a blueprint. Yeah, forget about that. You can try it out if you want, but yeah, I'd not worry about it. Okay, or you can tie it in with your animation blueprint, right? So you can set a variable and then grab the variable, and if she's walking randomly, then do snake dance, and then if she's chasing you, she's using the running scary clown walk, and then you randomly flip, random motion, she just, I don't know, stands in place and snake dances or something. It'd be horrifying for some of the models that you guys picked. Could be fun. So yeah, you just set a variable on her based on which one is being done. Create a variable, set it on her, and then in the animation blueprint over here. Animation blueprint over here. You could try to get the pawn owner. you could get the you can get variables off that, and then use that to modify which animation is played. Animation graph. There we go. So animation graphs are kind of cool. The ultimate result of an animation graph is the output pose. And so there's a lot of different things that are going in here that are done to pick between which pose is being chosen. So there's a state machine. The state machine says if she's in the air, then go to jumps. In the air is set here. It's a variable here. If she's not in the air, then it goes to the landing animation. Then after a certain number of seconds goes by. After 0.2 seconds, then it goes back to the idle jog animation. If we go into the idle jog animation, then it's going to be using cache pose ground loco, and ground loco. It's probably a blend space or something like that. Loco. Maybe we have to go back to. Yeah. So it's probably like one of these blend spaces that. Okay. So let's talk about math a little bit. Let's save out of this. Yes. So we learned today how to use high resolution art assets to import a new material. And we learned how to use nav meshes to create a character to navigate around. And maybe give a little bit of suggestion to have different animations when the thing's navigating down. Oh, thank you. Thank you. I did not make the wallpaper. So let's talk a little bit about math. Let's talk a little bit about math. Cracking people's passwords right now. There you go. Let's turn that off. Okay. So every semester I run a password cracker. See who's got bad passwords on my server. Then line rasterizer.cc. Okay. So last time we talked about a line equation, y equals mx plus b. Now we're going to talk about boxes. Boxes. Okay. Struct box. Double or int? Let's do double, I guess. Double x min, x max, y min, y max. Okay. Are you guys with me on this? So every box can be defined. You do it a couple different ways. You do x min and then x size, which is x max minus x min. You can have them stored as points. You can create like a point class, which maybe we'll do struct W2, which has double x and y as part of it, using point 2. So rather than 4 doubles, we could store it as like 2 points, point, min, and max, something like that. And then we've got a minimum point. It's like the top left corner, because 0, 0 is the top left. And max, which is the bottom right. Okay. Different ways you can do these things. There's always different ways you can do them. Okay. So why are boxes so important in video games? Well, as it turns out, there's circles and there's boxes, and that's about it when it comes to like and combinations thereof. When it comes to like doing like collision detection and things like that. Collision detection is one of the most important things in video games, and you want to know if something hits something else. And it all basically boils down to, you know, maybe maybe a convex hole, maybe a triangle, but you know, boxes and circles are the most important things if you're going to accelerate that. So let's say that you have a world of Warcraft. It's got lots and lots of triangles in it. And the player in the game clicks on an NPC. How do you know that you clicked on the NPC? Right? You have a camera. The camera is looking at the world. And the player clicks. How do you know what is in front of the camera? What function do you call to see what's in front of the camera at the point that the person clicked? How do you do that? How do you do that in Unreal Engine, let's say? How do you shoot a line from the camera towards a point and see what you hit? It's one of the most fundamental ways of interacting with the world. Okay. Yes, a trace line or a line trace, depends who you talk to. In Unreal Engine, it's called a line trace. In Quake, it's called a trace line. Same thing. So yeah, so you need to shoot a line from the camera towards the point on the screen. Okay. So how do you write code to do that? How do you make code such that you can take a line and hit the world quickly? That's an interesting question, right? Because if you can do that, if you can make it very, very fast to be able to shoot a ray out of your eye and impact something, then you can actually build a renderer around that. You can actually make a renderer that just shoots one ray out of every pixel on the screen, and if it hits red, then you draw a red pixel there. If it hits a green surface, you draw a green pixel there. And if you want to make it more complicated, you can make it reflect off mirrors. And if it's glass, you can have it, warp through it, do internal reflections, all this kind of stuff. But the most basic thing, we just need this to do interactions. If you shoot your gun, you're casting rays through the world. So, how do you accelerate it? How do you make that fast? Because you do not want to check to see if a ray hit every object in World of Warcraft. There's a lot of objects in World of Warcraft, most of which are nowhere near where you're shooting your gun or magical wand or whatever. Okay? How do you do it? What data structure do you use? For those of you that have taken 41, what data structure can hold data in such a way that if you query it with with a line, starting here, going to here, tell me the first thing that I hit. Which data structure do you know from CSI 41 would be able to make that go quickly? Dallin? Yui? Aaron? An array? For an array, you would have to kind of loop over the whole array and see if the line intersects the thing. I have the same 41 professor as Alexander. I wouldn't know. Wensix says heat map. My heart says instinct is wrong. The answer is none of them. Not a single one of the data structures in 41 would prepare you for this question. But I think I know what you're getting at, Yui. And when I wrote my game engine, I had just taken CSI 41, and I was placed in charge of making a 3D VR game engine. And so what I did was I made something like a hash table, if that's what you're getting at, Yui. So I made a hash table about 10 meters. It was a big 2D hash table, like an array, like maybe what Dolan was getting at. So you make a big 2D array, and every bucket is all the objects within that 10-meter zone, right? So if you have a building and a plant and a tree, which is, I guess, a plant, in one 10-meter area, when you shoot a ray through it, you just basically see if that ray hits any of those three objects. If it doesn't, then you figure out the next bucket, and you go through all the objects in that bucket. You go to the next one, and that is actually a workable data structure, as it turns out. As long as your world isn't like really dense and everything's not in one 10 by 10 by 10 zone, it actually works all right. If your world's pretty spread out, if you have a big open world, there's only going to be a couple objects within every 10 meter cubed area that you care about. The foliage you probably don't put into this. You just care about the landscape and buildings and things like that. It actually can work pretty well. And so how do you do intersection between a line and a box? How do you tell what spot you hit? Because if you have a 10 by 10 by 10 and the ray comes in, you also have to know where the ray goes out so that it can know where it comes in on the next bucket. Hash table, bows in doubt. Yeah, hash table is like almost always the answer if it's me. Or you could have said binary tree. So, how do you make a binary tree work with 3D data? Like map data? Like a binary search tree, yeah. Well, and we're gonna go over time, so Dolan, if you got to get to work or something, it's cool. But I'm gonna talk probably for another half hour on this. 8, 19, 21. So there's two questions for today. The first question is, if you got a square, we'll do 2D for now. Everything you do in 2D kind of applies to 3D, except for line intersection, I guess. Lines always intersect in 2D. They don't always intersect in 3D. So you got a box. You got a box. Got a box. And you got a line. How do you find out where it hits? Oh, you're off today? All right, cool. Where do you hit the box? How do you find that out? We got this equation here. This is like y is equal to mx plus b. We got over here x minimum, x maximum. We got y minimum and y maximum. Remember, top left corner is 0, 0. So how do we find out where we hit the box? That's one question for today. The other question is how you do a binary tree. Get the equation of the line for the four sides of the box and the line. Yeah, you can do line intersection. I've got a function on the server that can do that. But if you have a vertical line or a horizontal line, you can make it even easier. So let's say the minimum here is 5, the maximum is 10, the minimum is 5, the maximum is 10. Just make it easy, so that our box goes from 5, 5 to 10, 10. Now let's say our equation is y is equal to 1x plus 1. Okay, m and b are both 1. What is the value of this line when x is equal to 5? I want to make it match. Let's make it a plus 3. So I don't have to redraw my line. All right. Again, Mr. Yui, what is the value? What is the y value right here? What is that y value? When x is equal to 5, we plug in 5 here, right? And we get 8. So here, y is 8. You guys see that? Is 8 between 5 and 10? This spot here is 5. This spot here is 10. Damn it. I should have gone with 1. 8's lower. Sorry. I'll redo this. Whole upside down system. I'm going to make it 6. I'm going to 1x plus 1. There we go. Go back to your earlier answer, Mr. Yui. So this spot here is 6. So is 6 between 5 and 10? What do you guys think? Yeah? Yeah. It sure is. So does the line cross the box? Yeah, it does. So at the x minimum, if the y value, you just plug it in here, right? You do mx plus b. If the y value you get is between the x min and the x max, it hits it. Right? Do you guys see that? You just plug in x min into the equation, see what y you get. And if that y is in the goalposts, you know, if it's in the range, you hit. Cool. That's it. Yes, they touch. What point do they touch at? 5, 6. Right? X is 5, y is 6. We're shooting this from 0, 0. Then you probably do the tests left to right, you know, if you're shooting from 0, 0. And you can translate the whole thing. So like even if we're at 5,000 whatever, you can move it so that the shooter is always at 0, 0 to make this easy. You just subtract off our x and y position off of all these x, y positions. Makes life a little easier. Okay. We can do the same for all 4 of the edges. Okay. So we try x equals 5, x equals 10. What do we get for x equals 10? Damn it, the slope's going the wrong way. -1. Sorry, it's -1. Yeah, -1 plus 10 plus 11. I forgot. 0, 0 is top left, right? Not down here. This is not 0, 0. -1 plus 10, so we plug in 5. We get plus 11. Yeah. That's the equation. Okay. So our actual equation is -1 plus 11. So when x is 5, we get 6. Good. All right. Now let's plug in x is equal to 10. When x is equal to 10, what is y? -1x plus 11. So if we plug in 10 here, what value do we get for y? We get 1. So that means that this line on this line here, on that line, when x is equal to 10, it hits way up here at 1. Okay? So x is 10, y is 1. Is 1 between 5 and 10? Is 1 between 5 and 10? Big nope. So this is a miss. Because what you do is you just plug in the x max, and then you see if the y that you get is between x min and y max, right? It's not, so this one is a miss. This one is a hit. And then you can do the same for y min and y max as well, using the powers of algebra. And we'll get y equals 5 equals -1x plus 11. Subtract 11 from both sides. -6 equals -x, so x equals 6. Okay. So it's going to intersect here at 6. 6 is between 5 and 10. So that's a hit also. So we've got one hit at 5, 6. We got another hit at 6, 5. Okay. And since this one's closer to us, then that's the point that we hit. Okay. This is important because boxes are how most collisions take place in video games. In fact, have you guys ever heard of RTX video cards? They're these mythical creatures that nobody can find in the wild. An RTX video card. Have you guys heard of that? Like a 3090 RTX or a 3080 RTX or a 3070 RTX. Right? Have you wondered why they changed it from GTX to RTX? You know what the R stands for? They're a little pricey right now? Yes, they are. So you used to be able to get like a 1080, you know, GT or something like that, and then it became a 2080 RTX. So why did the G change into an R? Playing cards? Interesting. RTX. R is for mythic rare. Nice. Nice. Yeah, R stands for ray tracing. But what does that mean? Like, what does it mean for a video card to accelerate ray tracing? What is actually happening inside of it? What is it accelerating? How do you accelerate ray tracing? GTX was Gigatexel. That's cool. That's a cool name. More RGBs. Yeah. Yeah, they definitely have added a lot of RGBs to the RTX cards. But how do you accelerate this? This is a ray trace. You're sending a ray through a world, trying to see what it hits. How do you have your graphics card accelerate collision, which is normally handled on the CPU? The CPU normally has a list of all the objects in the world, and when you shoot a bullet, it normally goes through all the objects in the world. Somehow it's held in some sort of data structure, and it does these sorts of line box tests or whatever, and the CPU usually says, okay, you got to hit on this box right here. How does the graphics card do it? Does anyone know? It's a graphics card, right? It just draws pictures on screens. How does it do this? So the calculations is like draw it out. It actually does this. So what you actually do when you're doing RTX, when you have RTX on, right? You've seen all those memes like RTX on, and it creates these beautiful Minecraft, looks photorealistic and blocky at the same time, which is a weird decision. What you do is you send to your graphics card a copy of the entire world in box form. Okay? So what you send to your graphics card is, let's say you've got like a house or something. I'm going to draw a beautiful house here. Okay. What you send to your graphics card is you send a copy of all this, and it's held in something called BVH format, bounding volume hierarchy format. Which is a fancy way of saying boxes. You send lots and lots of boxes. So if you got your house here, what it's going to send is it's probably going to be like a 3D cube, you know, because it's a 3D game, but you know, 3D doesn't matter right now. Just talk about boxes. It sends one box that encloses the whole house, and then there will probably be a second box on the inside enclosing the roof, and a smaller box enclosing this part, and you know, I can color them like, so white is the outer one, red is the second tier, like that. And then it might have like a third tier, which would be like, I don't know. It might end up drawing a lot of boxes like this, depending. Something like that. So that's an acceleration structure. Yes, it is. And so an acceleration structure is any data structure that makes ray tracing go faster. Okay, so what happens is when you're here, this is you, and you shoot your gun this way, pew, 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 pew. There's only one box in this world right now, so it checks to see, does this gun you shoot intersect this box? It does what we did right here. What do you guys think? Does this multicolored laser we shoot intersect this box at all? What do you think? Done. That's it. Done. And your graphics card does that. It does linear algebra. It does that little bit of algebra that we just showed right there. Does this line, mx plus b, does it intersect at x min, x max, y min, y max? Nope. We're done. Return. False. Doesn't hit anything. That's it. And, I mean, there's like a function that runs if it misses and all this kind of stuff. But basically, it is like, nope, you missed. Sorry. Miss. That's it. However, if you shoot this way, Does that intersect the white box? Let's make this one a different color down here. It does. So now you got to do more work. So inside of the white box, there's two kid boxes, two children boxes. There's the red box and there's the green box. So we have to test this line against technically just the red box, but for the sake of simplicity, let's say we're going to test this line against the red box and the green box. Does our laser hit the green box at all? What do you guys think? Nope. Does it hit the red box? Yeah. And then, okay, inside of the red box, we've got a ton of other boxes. And when you get down to the leaf nodes, they're kind of held in different ways. A lot of times they'll allow like 10 boxes in one or whatever. Just depends on your settings. Does this multicolored ray hit any of the dark blue boxes? Miss. So that's it. So basically you have, one of the reasons why RTX graphics cards have so much RAM on them, right? Like 24 gigabytes of very high speed RAM, like almost as much as your system memory, right? Or maybe more than your system memory, right? My system has 32 gigs of RAM. My graphics card is like 24 gigs of RAM. Like, have you thought about how weird that is? Like your graphics card has almost as much RAM as your computer does. The reason for that is because you have to give the entire world, anything that you want to intersect with, anything that can be drawn, has to be on the graphics card, right? So you actually have to have this entire, like, if you have a bunch of things out there in the world, and they're all going to have boxes around them, okay, and all of those get shipped over to your graphics card, and then you can just be like, did I hit something? No. Did I hit something? Yes. Where did I hit it? Right there. And your graphics card can do that calculation, that hierarchical bounding box, where you have a bounding box inside of a bounding box inside of a bounding box. These boxes, by the way, are called bounding boxes because they kind of enclose your models. The graphics card can accelerate that very, very quickly. And it uses it to render. So what happens when you render something like that, it draws a ray. In every pixel of the screen gets a ray, oftentimes mostly more than one ray because you scatter them and things like that. But at the most simplest level, just think about you've got a 4K screen in front of you, right? At every pixel on the screen, it shoots a ray out of the camera, and the graphics card can tell you what you hit. So if your world is just like, let's look at it from the camera's perspective. So you got a house. It's completely green, I guess. And then this is your monitor. This is your 4K monitor over here. Basically, it'll sit there, and every pixel it shoots a ray, and it's like miss, 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 miss. It can do that very, very fast, and it can do it in parallel, right? Because it can send this over to processor 1, and it can send this part over to processor 2, this part over to processor 3, and you've got lots and lots of different processors on your graphics card at home that can all operate in parallel because all of them have access to that data structure. And so basically at every point it just sends a trace line out, and all of those are like black, black, black. Let's assume it's a black background for the sake of simplicity. And let's make the roof blue and the body green, whatever. And so all these are going to be black, but when it gets to here, it's going to be like hit. Okay, what did I hit? You hit a blue pixel. Okay, draw a blue pixel there. Hit, blue pixel, blue pixel, blue pixel, blue pixel, blue pixel. And then when you're miss, 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 miss. Okay, green pixel, green pixel, green pixel, green pixel, green pixel. And it can do this very quickly. That's what RTX means. RTX means it accelerates the ray tracing acceleration structure. It does that in hardware. Hardware can do things much, much faster than a CPU can. A CPU has to like sit there and load one command at a time and load things from RAM and do math and all this stuff. They have dedicated hardware specifically for this stupid little thing, right? That's it. It does this very, very quickly in hardware. Okay. And 3090 RTX cores. It's got 24 gigs of RAM. It's got 10,496 cores inside of it. Not all of those are RTX cores, though. RT cores, I think that's it, 82. So it's got 82 ray tracing cores. So it's got 82 processors running at once doing this operation. So it will split the screen into 82 different chunks, and each one of those ray tracing cores will accelerate the ray traces coming out of them. Okay. You guys understand? And we'll talk more about ray tracing later in the semester, but that's kind of the core idea, is that you've got a box and you got a line, and you want to see if the line hits the box. Okay. And if you have a complicated thing like this, then you have a box inside of the box. And you can have a box inside of the box, inside of the box, inside of the box, and it's boxes all the way down until you get to a leaf node, and then you eventually say hit or miss. So yeah, something like this. This is using circles instead of boxes, by the way. So like I said, circles are the other main thing. Circle is also very easy to see if you hit something or not. And so this is a hierarchical circular bounding structure, right? So you got the root one that holds the whole world, and if your line misses, you miss the whole thing. If it hits, then you figure out which one of these 3 subcircles it hits, and then if that hits, you go inside of it. If that hits, you go inside of it, and eventually you end up saying yes or no, I hit this thing, or whatever. So conceptually, do you guys understand that? That's pretty. And there's a lot of different ways of building them, and it's sort of more art than science to do a BVH. There we go. There's the famous MIT rabbit, I think it's called. So you see that there's like one box around the whole thing, and then there's sub boxes, and there's sub boxes within the sub boxes, and so on and so forth. So you guys got that conceptually? That's what RTX cores do. If I shoot a ray at that bunny, it tells me if I hit or I miss, or if I do hit, what I hit, what color is there. So that is ray tracing in a nutshell. All right, so let's come back over to here. And so I guess we can talk about BSP some other time. Just remind me of that. It's a binary tree instead of this. It's a different way of holding things in a world. So BVHs are probably the most common, and they're just a bunch of boxes. So and these boxes are all what are called axis-aligned bounding boxes. So you'll see this if you guys work in the industry. You will see people talk about AABBs all the time, and they will just call them an AABB. And you will look like a dum-dum if you don't know what it means. Like, what is an AABB? I thought you were a graphics programmer. How do you not know what an AABB is? I know my ABCs, but I don't know my AABB shishis. So, an axis-aligned bounding box. What does it mean, axis-aligned? That means that you got a vertical line, you got a horizontal line. That's it. If it's not axis-aligned, that means the box will be rotated, and that makes your math harder. Doing line segment intersection, intercept. So I got this off Geeks for Geeks, which is not a great website, by the way, but whatever. I just copied it. This is the code to see if one line intersects another line. Right, so you got these like multiplies and subtracts, and there's a lot of different ways you can do line-line intersection, but this is one of them. And so there's a lot of stuff that goes into that. That's why people prefer, Geeks for Geeks. Just be careful when using Geeks for Geeks, because it's not got a great reputation for being accurate, especially when it comes to like C++. There's a lot of bad code on C++ on Geeks for Geeks. So yeah, I haven't even really tested that one out. I actually don't even know if it works. I was just kind of messing around. So yeah, and so rather than doing all that nonsense, you can do a collision with a box real easy. You just try plug in, you know, plug in the thing, and plug in X for X min, plug in X for X max. See if the Y that you get is between the Y min and the Y max. That's it. And then do the same for X min and X max. That's it. So if we want to construct a line, or we can do a line segment. Let's not worry about it for now. Yeah, why not? Okay. Construct line. That's it. Okay, so please enter N, please enter B. Yeah, let's pull that code out into a function. Void raster. So we just draw the line on the screen like this. All right, those need to be set. Okay, so I'm just refactoring this code so that I can actually do something kind of funny here. Read, please enter. Yeah, whatever. We can actually embed these inside of the thing here. That's fine. Okay, so we're going to read M and B. We're going to make a line out of it, and we're going to draw the line. So it's basically the same code we had before. We're just kind of putting it into a class. And this still has the bug where this one uses the bottom left corner, so we'll pull that out there. So everything will just use the top left corner as 0, 0, like the Lord intended it. And it's anti-aliasing if the thing is flatter, and it's not anti-aliasing if it's steeper, which, whatever. It'll be interesting at least. And yeah, so these don't need to be there. Okay, so we've got a class now that holds a line, and we've got the ability to draw the line. So let's just test to see if this works. So G++ line rasterizer.cc, run it. There we go. Got a 45-degree angle. Cool. Cool. 0.1. Cool. So it anti-aliases when it's flat. It doesn't anti-alias when it's steep. Who cares? All right. All right. So we need to do what we're saying we're going to do today, which is to see if a line hits a box. Or we can add box rasterization. Do you want to see box rasterization? Draw a box on the screen. Sure. Okay. So a box is just 4 lines. So I actually don't need to write new code. Attack the boxes part 2. Yeah, the Terminator boxes. You could probably animate them. Like clear the screen, draw, clear the screen, draw, you know, and actually have the boxes chase you around. There is mouse support in Putty, so you can actually make a top-down shooter or something. All right. MX plus B. All right, so now we'll do double X min. Read enter xmin, yy3p, x max, ymin, x max, no y max, sorry. And it's over here. All right, so we're going to read an xmin, x max, ymin, y max, and then we are going to make a new box called box. Anyone got a better name for a box? Sorry, I'm out of ideas. We need to make Doom run in the command line. Yeah, I mean, we did that with you, right? Yeah. Carden. All right. Milk carton. Let's go with carton, it's shorter. And so we'll initialize that with xmin, ymin, xmax, ymax. Okay. So remember, we chose to do our boxes with 2 points, one holding the minimum, so that's going to be min x and min y, and the other holding max, which is going to be x max and y max. Okay. So we made a command line runner. So let's do a raster, void raster. So let's have the ability to draw a box. So we're going to draw a line, then we'll draw a box. Okay. And a box is just 4 lines. So that should actually be pretty easy. So line 1. Again, I'm stymied on coming up with a good name. Okay, so line 1 is going to be how do we do vertical? We can't do vertical, can we? Huh? We're going to need to pass in nan, aren't we? For the slope. Can't have an infinite slope, right? Can we handle an infinite slope? Or should we make a magic number? Okay, so if we have a vertical line, okay, if is nan m, so if our slope is infinite, and that's steep. And for you, no, we need to do line segments, don't we? Yeah. We need to do a line segment, not just a box. So the boxes will be infinite if we do lines with them. So yeah, let's not worry about that then. We need to make a line segment class first, and then we can draw it that way. So rather than doing that, we got 3 minutes left. Let's do the collision test. So bool collide does collide. I don't know, collide with a line named L, which looks like a 1. So return true if the line intersects the box. Okay. So down here, the person's entering a line, they're entering a box, and then we return true if the line hits the box. Okay, so out bool alpha, does the line hit the box? Carton dot collide with y. You guys understand what we're doing here? So for main, we're entering a line. For box, we're entering a box, and then we're going to print out whether or not the line hits the box. That's the math for today. You guys understand? Ready to go? Okay. Well, let's just do it. So if we want to see if the line hits, then we're going to just make 4 checks. So check to see if the line, let's call it Li for consistency, hits the left edge, the right edge, the top edge, the bottom edge, which is covered up by my face. Okay. So all right, so test 1, line dot m. Yep. M times x, min dot x. So that's our left edge, right? Plus line dot b. If test 1 is between our minimum y and test 1 is less than or equal to our maximum y, return true. And then we're just going to repeat this 4 times. So this is for the left edge. This is the left edge test. Right? So this is just mx plus b. The x that we're using is the left edge of the box. So we just plug in that left edge of the box, whatever x value that is, we're plugging that into mx plus b, and we're getting a y value. So if the y value we get is between the minimum and the maximum, it's a hit. You guys got it? We just do this 4 times. Okay. So the max x is the right edge of the box. Do it again, see if it's in between the bounds. Then we're going to do the top edge, which is going to be double x is equal to the line, what is the algebra again? Did I close it? Guess I closed. So let's see. If y is equal to mx plus b, then x is equal to y minus b divided by n. So we plug in the minimum y value to get the top edge. Yep. So it is minimum y value minus b divided by m. It's this right here. So if we want to see if it hits the top edge, right, we plug in the minimum y value, in this case 5, and then we check to see if the x value we get out is between x minimum and x maximum. So if x is greater than or equal to min.x and x is less than or equal to max.x, return true. And do the same for the bottom edge. Technically, I think you can skip the bottom edge because I don't think a line, every time a line hits a box, it's going to hit two sides, right? So I think you can skip the bottom one, but whatever. We'll do it for completeness. Declare X, so max Y. And if this is greater than or equal to that, I think that's it. That's good. Okay. Oh. And then if it passes all of these things and doesn't anything, return false. Missed all four edges. So if we have a slope of 1 and a y-intercept of 0, did we not compile it? What's going on here? Oh, it draws the screen. Right. Let's not draw the line. We don't need that. And let's turn that off for now and turn off that for now as well. Okay. Okay, so slope of 1, y-intercept of 0, x-min is x-min? X-min. 4, 4. Ah, damn it. Slope of 1, y-intercept of 0, x-min of 1, x max of 10, y min of 1, y max of 10. It hits the box. Okay. Now if we have a slope of negative 1, 1, 10, 1, 10, it misses. Okay. So with a slope of 1, it hits. With a slope of negative 1, it goes this way, right? And it misses the box. So there you go. So that little thing right there, this even though this looks like basically nothing, right? Like, you know, it's just really, really simple line intersection tests, which are really easy if they're horizontal or vertical. Horizontal and vertical line intersection tests are trivially easy. You see how easy this is? It's super easy. That's why we use axis aligned bounding boxes. So they're all vertical or horizontal. Don't have to do any fancy schmancy stuff. Okay. So that's it. So that right there is what enables like all of ray tracing on all these fancy RTX hardware cores and things like that. You just do this a lot of times. Okay. So your homework again is to make a bot that runs around in the world. Is it possible in having to use using something to automatically do it 4 times if the 4 are doing something relatively similar? Yeah, you could probably do this with a single SIMD instruction. Rather than this, you could probably pack all 4 of those multiplies into a single SIMD instruction, which you'll learn about in CSI 45. Right. You know, when I'm doing all of these things, I am not claiming this is the fastest way to implement it. I write my code so that it's as easy as possible for you to understand. So I draw a little box and do the thing and show where it hits. This isn't, nothing I do is designed to be like optimally fast. It's all designed just so you understand the concept. Once you understand the concept, then you can work on it and play around with parallelizing it and stuff like that. Yeah. The observation here is that you're basically doing the same math, you know, twice, and you're doing this twice. And if you're doing the same math twice, then you can do what's called a SIMD instruction. SIMD, which allows you to do 2 of them in 1 cycle. And probably if you were smarter than me, you could probably do all 4 of them in 1 cycle. Not really sure how exactly, but you could probably do all these in 1 cycle, and then the comparisons. These comparisons probably can be done in 1 cycle. 2 of them can be done in 1 cycle. So you could probably do all of this in 2 cycles, all of this in 2 cycles, and if you're smarter than me, I don't see how, again, you might be able to do this whole thing in 2 cycles. So, yeah, but this is not optimized. It's just to demonstrate what's going on. That's why I put comments in here and stuff like that. All right, so work on your homework assignment, everyone. I will see you on Tuesday. Have fun playing with Unreal Engine, and maybe next week we'll get to our first actual program on the server. I've been talking a lot and doing a lot of coding on the server without having you guys do anything on it. So I'll probably switch over to the server maybe next week. We'll see how that goes. Okay? All right. That's it. See you guys.